Hi, this is Maolin from UC Merced. Today I'm gonna introduce DrGPU memory, a profiler to guide memory optimization for GPU applications. Nowadays, GPUs are widely used to accelerate applications in various domains, such as molecular dynamics simulation in pharmacy and virus analysis. However, these GPU workloads require ever-increasing GPU memory resources. So, the limited GPU memory capacity is often a major bottleneck in fully utilizing GPU computing resources. For example, GPT-3 has 175 million parameters and requires 800 GB of memory for training, but the latest H100 only has 80 GB of device memory. It's a large gap. GPU memory is primarily managed by the following 5 GPU memory APIs. CUDA-malloc allocates a chunk of device memory. CUDA-free reclaims a chunk of device memory. CUDA-memory copy copies memory between the device and the host. CUDA-memory set sets the device memory to a specific value. CUDA-launch kernel launches a compute kernel on GPU. Here is a motivating example showing unused allocation in PyTorch. PyTorch is a popular deep learning framework. As we can see, tensor columns is allocated at line 2 and is only used at line 8. On line 8, there is a ternary conditional operation. If requires columns is true, tensor columns is used. Otherwise, tensor columns is not used. So, tensor columns sometimes is just allocated but not used. This definitely wastes the limited device memory resources. We call this kind of memory inefficiency unused allocation. To eliminate unused allocation, we allocate tensor columns only when requires columns is true, as highlighted in the green box. The second motivating example is from MiniMDoc. MiniMDoc is a molecular docking tool, and Pmain conformations is a GPU array. It's always allocated with a maximum memory size as highlighted at line 2, but it initializes the same array based on the actual input size, and it only uses the initialized part of the array as highlighted at line 9. The allocated memory size is often larger than the actual used memory size. That's to say, there is a chunk of memory in the array that is allocated but not used if the input size is not equal to the maximum size. So, we can use the actual input size to allocate the device memory to eliminate the memory wastage, as highlighted in the green box. Besides the previous two applications, we investigated many other important GPU applications and found GPU memory inefficiencies that can be categorized into object-level inefficiencies and intra-object level inefficiencies. For object-level inefficiencies, we focus on the order of GPU memory APIs on each object, but do not care about the memory access on each element. For intra-object inefficiencies, we focus on memory access within a single object. Object-level inefficiencies can be further classified into early allocation, late deallocation, redundant allocation, unused allocation, memory leak, temporary idleness, and dead write. Intra-object inefficiencies can be further classified into over-allocation, non-uniform access frequency, and structured access. Due to the time limited, I'm gonna illustrate the late deallocation and temporary idleness only. For more information, please refer to our paper. Here is the timeline, and we use different shapes to represent a set of GPU memory APIs. A square represents a CUDA-malloc, a star represents a CUDA-launch kernel, a circle represents a CUDA memory copy, a pentagon represents a CUDA memory set. A triangle represents a CUDA free. For example, object 1 has CUDA-malloc at timestamp 0, The first CUDA memory copy at timestamp 1, and the first kernel access at timestamp 6, and the second CUDA memory copy at timestamp 9, and CUDA free at timestamp 10. From the timeline, we can see there are multiple GPU memory APIs between the first CUDA memory copy and the first GPU kernel that access object 1. That's to say, object 1 is idle from timestamp 2 to 5. We call object 1 suffers temporary idleness from timestamp 2 to 5. For memory saving, we can move object 1 to the host right after timestamp 2 and bring it back right before timestamp 5. We can see that object 2 also has the same pattern from 4 to 7. For object 3, the last kernel access is at timestamp 8, but it's not released until timestamp 12. We call this kind of inefficiency late deallocation. For memory saving, we can invoke CUDA free as soon as no kernel accesses object 3. This table summarizes the aforementioned memory inefficiencies in popular GPU applications such as PyTorch, Lagos, .NET, and so on. You can see that they are prevalent, especially for early allocation, late deallocation, and temporary idleness. To detect the aforementioned memory inefficiencies, we propose DrGPUM memory. DrGPUM memory takes the GPU binaries as input and includes 3 components: an online analyzer, an offline analyzer, and a GUI. DrGPUM memory targets fully optimized, unmodified GPU binaries. The online analyzer intercepts GPU memory APIs and instruments GPU memory instruction. It also records call paths and analyzes the inefficiency patterns. The offline analyzer annotates profiles and highlights problematic objects. Finally, the GUI shows the GPU memory APIs in the timeline and provides optimization suggestions. Next, I will dive into the core component, the online analyzer, to illustrate the object-level analysis and the intra-object level analysis. For object-level analysis, it intercepts every GPU memory API and analyzes the APIs in the timeline. For intra-object analysis, it instruments every GPU memory instruction and investigates the memory access information within a data object. DrGPUM memory finally reports memory inefficiency patterns and optimization guidance. Next, I'll talk about the challenges during the profiling. DrGPUM memory supports the multi-stream applications by constructing the dependence graph. We extract the read after write, write after write, and write after read data dependency and the launch dependency within a single stream to construct the dependence graph. DrGPUM memory also supports custom memory APIs. For example, PyTorch uses custom memory APIs to allocate device memory from pre-allocated memory pool. DrGPUM memory supports PyTorch's custom memory APIs. To reduce the profiling overhead, we add kernel and block sampling, as well as kernel whitelist for intra-object analysis. Kernel and block sampling is based on the similar behaviors across different instances of the same GPU kernel. Whitelist enables developer monitor the kernels that they are interested in. We move the analysis from CPU to GPU to accelerate object-level analysis. Next, I'll talk about a case study, Simple Multi-Copy. Simple Multi-Copy is a multi-stream program from CUDA Toolkit examples. Here is a screenshot of DrGPUM memory's GUI that visualizes the profile of Simple Multi-Copy. The top pane shows the order of GPU APIs on different GPU streams. In this example, there are 5 streams. The middle pane shows various data objects along with GPU APIs that access them. When users click on a GPU API, the bottom pane will present intuitive optimization insights, such as call paths, optimization suggestions, and so on. Guided by DrGPU memory, we found object the data out1 suffers early allocation. For optimization, we allocated it just before kernel 01, and we gain a 50% memory consumption reduction from simple multi-copy. Guided by DrGPU memory, we optimized many well-known HPC and deep learning workloads, such as PyTorch, DuckNet, Lagos, and MiniMDoc, and gained significant peak memory consumption reductions. In the diagram, the vertical axis is the memory saving percentage, and the horizontal axis is the different GPU applications. We can see that we can get about 50% average memory saving among these GPU applications. In conclusion, we found various forms of memory inefficiencies such as early allocation, late deallocation, and temporary idleness, which widely exist in GPU applications. We deal with these issues with DrGPU memory, the first profiler systematically investigating memory inefficiency pattern in GPU applications. DrGPU memory helps developers investigate GPU memory inefficiencies and opens a new avenue to tool applications for inefficient use of memory. Our tool is open source under a BSD 3 license. Thank you for your attendance. I'm happy to take any questions.